Chapter 4: Current, Voltage, Resistance, EMF, Power, and Circuits. Current, voltage, and resistance. So this part of the slide, it is just talking about the definitions and the differences between the terms. Like the first one, current is just the flow of electric charge in the unit of ampere or A. So that is the definition of current. And for the resistance, is how much an object opposes the flow of a current. The unit is ohms. And most of the time, these are the value that you see in some of the resistors. Like for example, if you have a resistor, let me draw that resistor. Mm, like for example, if you have this resistor like that, and it has this like squiggly body like that. Okay, they have these stripes, and those stripes indicates the measure of the resistance. So it is already given in that resistor that that is the value of the resistance. While resistivity is a measure of how strongly a material resists the flow of the electric current. So you can just think of resistivity as the actual resistance of the material itself. That is not entirely intended for us to be rated as the resistance, because in the resistance it's actually the one that is rated, that is already measured, and we are already aware that's how much the resistance is. But for resistivity, it's the resistance of the material itself, like how the material resists the flow of charges or the flow of the electric current. So that's resistivity. So that's the difference between the two, but they are related to each other. In resistivity, the unit is in ohms meter because it's indicating that the resistance created per material. So the longer the material, the higher the resistance it creates, or other factors that could lead to production of heat. So resistivity is the one reason why sometimes we can feel that the wire is already warming up, especially if you're using like a tiny wire or a long, very long wire. So those are materials creating their own resistance. So that's what we call as resistivity. Okay, resistance is the one that we already know, that is already put there as a rated resistance value. But resistivity is the one that will be uh, getting from the materials that we are using. Okay, or even the load that we're using, the whatever devices that we're using, they could create their own resistance, and that's what we call as resistivity. Okay, so I hope that you remember the difference between the two. So resistivity is directly proportional to temperature. So whenever the temperature increases, resistivity increases. Or if resistivity increases, especially if you're using very tiny, thin wire, it means the resistivity in that case is increasing, then the temperature also increases, and that's the cause of burning up, or you burn your wires. Okay, so they are directly proportional. It means one increases, the other one increases as well, and vice versa. If resistivity decreases, making the wire thicker, then the temperature will be cooling down or lesser. Next, voltage. Voltage defined as the push that moves charge between 2 points, and the unit is volt. Okay, and we have these other volts as well, unit volts, the voltage drop, and also EMF. So what is voltage drop? Okay, we will be using this most of the time. If we say voltage drop, these are the voltages that are used up from one point to another point, especially in resistors or devices. Like what is the voltage before and after it is already used that from that device. Like for example, the resistor is using this V amount or voltage amount, then that is the voltage drop. Okay, so voltage drop is the portion of the voltage used up across a component, especially most of the time that we're using in the component resistors. Okay, but you can apply that to any devices, any device that use electricity. EMF is the total push provided by the supply source. So this is the voltage found in the supply source. So make sure that you remember EMF is the voltage that is responsible in pushing the electric current from the supply source. Okay, so that is the EMF, and most of the time, because we're using the battery or dry cells in our circuits, so it's from the battery. That's the EMF. Okay, current density. Okay, the words might be something new from you, but this is just how much density flows per unit area perpendicular to the direction of the flow. So what does it mean by this? It means how much of this charges pass through this area here, this flat area of circle. That's why we call this as cross-sectional area. So how many of these charges pass through this area? And that is what we call as the current density. Okay, so pass through this area at a time. Okay, and the formula for the current density is J equal to I over A. So J is the current density, I is the amount of current, and the A is the cross-sectional area. And why is it saying perpendicular? It says perpendicular because look at the circle here. The circle is flat, perpendicular to the direction of the current. That's why it's perpendicular. It means the flatness of the circle is not along the direction of the electric current. Okay, and that's what we call as the cross-sectional area. So the relationship between them, and relationships can be determined by looking at the formula. So if you look at the formula, this is the density, right? The J is the density. Okay, let me erase that. Oops. So J is the density. So density is directly proportional to the current because both of them are in the numerator. So J is numerator. Assume that there's a denominator 1. So J is numerator and I is also numerator. Then they are directly proportional. So remember, you can only do that if they are on different sides of the equation. So J is on the left side, I is on the right side, and they're both numerators, then they are directly proportional. That's why it states here that current, I, is directly proportional to current density, J. So it means the more current that you have, the greater current density that you will also get. Okay? The lesser current that you have, the lesser current density that you will get as well. As long as all other factors are constant, especially the cross-sectional area is not changing. If we're comparing these two, it means the other variables must be not changing. We're talking about the cross-sectional area. Now, in the second one, cross-sectional area is inversely proportional to the current density. This time we're talking about the relationship of this and this. So it says inversely proportional, and why? Because J is in the numerator and A is in the denominator. And remember, cross-sectional inversely proportional means if the cross-sectional area is bigger, current density is smaller. Okay? So if this cross-sectional area is changing into a bigger area, then this density decreases because they are inversely proportional. Or vice versa, if this cross-sectional area decreases, becomes thinner, the wire becomes thinner because it becomes smaller cross-sectional area, then the current density increases. Or lang siya maghuot sila ba? Mo nang mo concentrated siya, mo nang density mo dako. Kung mo gamay ang wire. Okay. Electron flow versus conventional current flow. Okay, I already mentioned this during your PT orientation. So if we say conventional current flow, this is the one that we're using, especially in our circuits. Okay, conventional current flow, we're talking about the current moving from positive, look at this, from positive terminal to the negative terminal. So it's from this flat here, this is our positive, and it's moving, going to the negative terminal. Okay, whatever your device is here, it could be a resistor, it could be a bulb, anything. So it doesn't matter as long as the flow is from positive going to the negative. That is our conventional current flow. And if it is conventional, if it says conventional, it means that's the thing that we're gonna follow for all okay, for all who ever use the series parallel circuits. Okay, so that's why it's conventional. It means we're sinabutan ba nga kailangan ka na atong i-follow. Next, electron flow. Electron flow is the movement of the electrons, and it is said that it's from the negative terminal of the battery going to the positive terminal of the battery. And of course, we're not using that because, again, ang nasabutan kay kani atong gamiton. So we're gonna use the conventional electron current flow. Okay, now let's go to the Ohm's law. The Ohm's law is now the combination of those two important variables, the V voltage, the I current, and the R resistance. So the first formula that comes up in our mind if we hear the word Ohm's law, it's V equal to I times R. And remember, Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference, which is the V, across it. So provided that the temperature and other physical conditions remain constant. Why? Because if these are not constant, there will be a chance that non-ohmic happens. Okay, so as long as these temperature and other factors are not involved, we will be following the ohmic method. So the device will be following the ohmic method, which is the V is equal to IR. Okay, and the V equal to IR could be manipulated into a different way depending on which one is being asked. So if you're asked for the current, so you can manipulate the formula and it becomes I is equal to V over R, and for resistance, R is equal to V over I. Okay, so keep in mind, voltage is directly proportional to current. So why? So voltage here and current here, so they are both in one place, numerator and numerator. That's why they are directly proportional. The same thing for voltage and resistance. V and R are both in the numerator and numerator. Now for current and resistance, they are inversely proportional. Now you might be asking, why are they inversely proportional? They're both in the numerator. Again, the condition to get the relationship of the two variables, they need to be in opposite side of the equation. So we're gonna find, oh here, this one. I is on the left side, R is on the right side. So they don't have the same position. I is in numerator and R is in the denominator. And the same thing here. R is in the numerator, I is in the denominator. So whatever manipulation that we do, current and resistance are always inversely proportional. And remember, if it is directly proportional, whatever increase of the one variable will be the same increase of the other variable. So their graph is like this. So when the first variable increases, the other variable increases as well. And the same thing if we go in different direction. If it decreases, the other one decreases as well. But for inversely proportional, the graph is a curve. I'm sorry, it should be a very clean curve, but I mistakenly drawn the curve. Okay, so it's a curve graph for the inversely proportional, okay, because it's going the opposite way. So it's getting smaller and smaller if we multiply the one variable, multiply bigger and bigger, the other one becomes smaller and smaller and smaller, approaching to zero. Okay, so what happens in the inversely proportional? Multipliers are reciprocal of each other. So what does it mean by that? Let's try the directly proportional. It's easy. If whatever you multiply to V, the same thing you multiply to I, because they are directly proportional. So if I have 5 times V, the I becomes 5 times as well. So it's just like that. But for inversely proportional, like for example this one, I made my I 2 times, twice, my R becomes 1/2. And why is it 1/2? It's because the multipliers must be reciprocal with each other. So if I multiply 2, which is 2 over 1 to I, you flip that 2 over 1, it becomes 1/2, and you multiply that to the other variable. And that's what we call as reciprocal. Okay? So the same thing here as well. If I multiply 5 over 3, or 5/3 to I, you'll multiply 3/5 to R, because they are reciprocal multipliers. Okay? So that's how you perform changes, if ever you change the value of I into twice, what's gonna happen to the R? So that's the thing that you'll do if it is for I and R, because they are inversely proportional. But if voltage and current, voltage and resistance, whatever you multiply to voltage, the same thing you multiply to resistance. Whatever you multiply to voltage, the same thing you multiply to current. Okay, so that's it. Now let's test the Ohm's law with this problem. A series circuit has a total current of 0.5 amperes and is connected to a 9-volt battery. Two small bulbs are connected in series. So what is the voltage drop, or the voltage, across the first bulb, or the R1, if it has a resistance of 10 ohms? Okay, now, of course, since there are two bulbs, it means there are two R's involved, R1 and R2. You might be thinking that we're gonna do, of course, all the totals. We put all the totals here because we already know the current flowing in the entire circuit is 0.5, so the I total is 0.5 amperes, and the V total is 9 volts because it shows here it's connected to the battery. The EMF is 9 volts. So V total is 9 volts. And we're figuring out the RT, and we can solve that using the Ohm's law, right? Now, there are two valves, so we might think, oh, we're going to put V1, I1, R1, and V2, I2, R2. Okay, that's great if you have much time, more time. But since it is only asking for the first valve, it means we're only involving the R1 group. So we don't need that. We just need to solve this. Okay, so we have 10 ohms for the R1. And remember, this is a series circuit. In series, we have a condition that all I's are equal, and we're gonna do that later on. So 0.5 amperes for the I, and we can now solve for the voltage here. Okay, so we're looking for the voltage drop. There's no need for us to get the total R here because that is not what being asked. You can get the total R if you want to, but that's not what being asked, so there's no need to get that total R. So let's solve for the voltage using the Ohm's law. So V is equal to IR. We already have the I and R, and you just multiply them and you got the value 5 volts, and that's the answer for this question. There's no need for you to fill the other other missing values up because that's not what is asked in our question. But if you want to, you can actually just solve this like automatically, like if you're in the zone, that's fine, as long as you answer the one being asked, and that's it. So V1, the voltage drop, it means the voltage used by our R1. So that's the one that is being asked, and that's your answer for that problem. Okay, now let's start with the series circuits. Electric circuits where components are arranged in a single continuous path, just like this one. If you look at them, if we start from the positive terminal and move going back to the negative terminal, we can see that they are arranged in one path, right? And this is what we call a series circuit. Now, the conditions that you need to know if you have a series circuit is all the voltages are added together to get the total voltage, or the amount of voltage here from the source, or the EMF. Next, the total current or electric current are equal to each other. So the total current is equal to the current 1, current 2, and current 3, and so on. And last one, the total resistance is just the sum of all the R's, okay, of all the resistance in the circuit. So if we have R1, R2, and R3, add them up, and that's your total resistance. Now, if we have this example and you are asked, what is the current and the voltage drop, or the voltage in resistor 2? Okay, remember, voltage drop, it means that's the voltage used up by the certain component, and here it's stated that the component that is mentioned is the resistor 2, so it means this one. So how much voltage is being used in this resistor 2? So we have already the resistance for all of them, the 2 ohms for the resistor 1, the resistance 2 is 4 ohms, the resistance 3 is 10 ohms. Okay, and that's what I mentioned as well a while ago. If we say resistance, that's the calibrated resistance, like the rated resistance of the device. And if it is resistivity, it means that's the resistance created by the materials. Okay, that will be calculated if we solve the resistivity. But here, these numbers are resistance because they are already rated, or they are already calibrated as that amount of resistance. Okay, anyway, let's go and solve for the voltage drop and the current in resistor 2, or the R2. And of course, our method is, of course, if we have four of the components, three components for the resistors, and the battery source, that's the fourth component. So if we have four components, of course, we're gonna do this, the total. We're gonna put the ones for the R1, and the twos for the R2, and the threes for the R3. Now, it will take us like a lot of time if we do this, especially if the question is just this one. Okay, the trick here is don't worry about the rest of them. Since we are only concerning on the resistor 2, so we're just going to focus on resistor 2 instead of solving all of them. Okay, so here, put all the known variables that we values that we already know. So we have the 20 volts, the EMF, which is the total voltage. So put that there, 20 volts. And what else? Since we're only focusing on the R2, so the value of the resistance in the R2 is 4 ohms. Okay, so those are the given so far that we can put here. But the question is, which of the other variables that we can get out of the given here? The total resistance, of course. And in series, the total resistance is just the sum of all the resistors. So we have all the resistance here in our series. You just need to add them up, 10 up to plus 4 plus 10. That's 16 ohms. So that's our total resistance, and that's it. Now, we have already two variables given and one unknown. We can now use the Ohm's law. Remember the Ohm's law? This is also the Ohm's law. We just need to manipulate it so that the I is on the left side, and V will be divided by R to get the I. Okay, so solve this. V divided by the R, 20 divided by 16, and the answer is 1.25 amperes. Now, is this answer helping us to get the answer for the resistor 2? Yes, it's because I total is equal to I1, equal to I2, and equal to I3. So it means that the I2 is also 1.25 amperes. So we already have one answer in our question. Let's find the voltage drop or the voltage in resistor 2. So how do we answer that? Of course, the Ohm's law. Don't forget that the Ohm's law is very useful. And how to get that 5 volts? Using the Ohm's law formula, V is equal to IR. So we have 1.25 times 4, and we got the answer, 5 volts. Okay, so that's how you do series circuits. Now, how about parallel circuits? Now, look at the shape of the parallel circuits. They are not in one path. They have their own path. So that is parallel circuits. So each resistor is connected across the same 2 points, providing multiple paths for the current to flow. So the current, this is 5A, can flow this way and that way, can flow this way and that way. So it has multiple paths to flow. Okay, that's what it means by parallel circuits. Now, the condition that you need to remember for parallel circuit, the voltages this time are the same for each path. Okay, so voltage, which is the EMF here, is equal to the voltage 1, the one going this way, which is, we only have R1, so it means this is the voltage 1 here, equal to the voltage 2, which the voltage drop used here, and equal to the voltage 3, the voltage drop used here. Okay, next, this time the I total is the sum of all the current passing through each device. So it's now the opposite. In the series, all the I's are equal, but this time in parallel, all the V's are equal, but the I's will be added up. Now, the R in parallel is the most challenging one. Why? Because it is the sum of all the reciprocals of R. Okay, so 1 over RT equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Okay, so that's how you get the RT. And of course, there will be an added step for you to really get the RT here. You're gonna flip it, okay? And we're gonna perform that. Now, the question here is, what is the current and voltage drop in resistor 3? So we're now focusing on resistor 3, this one. We're going to ignore these, but we're going to use their numbers to solve for some of the variables. Okay, so we're going to put the total. Of course, the total will always be helpful, so we're going to put that all the time. And the R3 groups, or the threes variables. So we have the values 5 amperes, which is it is from the voltage source, so it means it is our I total. Okay, and we have as well the R3, because that's the one that we're gonna focus. And obviously we have 8 ohms and 4 ohms, but that's for R2 and R1. If you want to solve that, it's up to you. It will take you more time. Okay, put the R3, which is 2 ohms, and this time let's find out some other given that will other values that will be solved using the data that we have in our diagram. We can find the total R, right? But not like the series. The series, you just add them up and you can get right away the total R. But here in parallel, you need to do the sum of all the reciprocals. So solve them using this. So, and look at this. Which of the resistors here has the smallest resistance? It's the R3. And we're going to expect that the R total must be smaller than the smallest amount of resistance in our circuit. So it should be smaller than 2. So let's try if it is true. Okay, we add 1/4 plus 1/8 plus 1/2 because R1 is 4, R2 is 8, and R3 is 2. So these are the reciprocals. Find their LCD. Their LCD is 8. So 8 divided by 4 times 1, that's 2. 8 divided by 8, that's 1 times 1, that's 1. 8 divided by 2, that's 4 times 1, that's 4. So that's why we have these numbers. I hope you still know how to do LCDs. And add them up because they now have the same denominator. So 2 plus 1 plus 4, that gives us 7. Okay, and that's 1 over RT equal to 7 over 8. That is not the one that we're looking for. We're not looking for 1 over RT. We're looking for RT. So we're going to flip both of them. So RT will now be on top. 1 will be now at the bottom. 8 will now be on top. 7 will now be at the bottom. And simplify. RT divided by 1 is just RT. 8 divided by 7. The answer is 1.14 ohms. Or you can just use 8 over 7. That's fine. But some of the choices in the test might be in decimal form, so you need to transform them into decimal form. So we already have our total R here, and look at our total R. The total R is smaller than the smallest one in the individual resistance in our circuit. That is always true. Okay, keep that in mind. That is always true. The smallest resistance in our circuit should be bigger than our total resistance. Okay, so it means the total resistance must be smaller than the smallest resistance in our circuit. Okay, so put that there, 1.14, and we can now solve for our VT, our total voltage, by using the Ohm's law, multiply the I and an R, and we can get 5.7 volts already. And we're going to use that, of course, because voltage in parallel are equal to each other. So V3 will now be 5.7 volts. So we already got the voltage dropped in R3, that is 5.7 volts. Okay. How about the resistance? Of course, you need to solve it using the I is equal to V over R. This is still Ohm's law. You just need to manipulate the formula so that the I is now on the left side. And V, which is 5.7 divided by 2, the answer is 2.85. Oops, sorry. That's supposed to be amperes. That's my bad. A. Okay, that's amperes. Because it's I, it should be amperes. Or A. Okay, that's how you solve for the parallel circuits. Now how about this? I know this one sometimes it scares you. Like, what is this? This is no longer simple. Yes, of course, because this is what we call as complex circuits. And there are a lot of complex circuits, and some of the circuits are used as puzzles for all the circuits enthusiasts out there. If you love this kind of puzzles, you can actually solve this. The first step that you need to do is just to make the circuit simple. That's the first step. Okay, for example, this circuit here, they look like a parallel, right? They almost like a parallel. So we can simplify this by turning this into a simple parallel circuit, right? So how to make this into a simple parallel circuit? Look at these two resistance here, this and this. They are in series. They're in one path. It means it is going to follow the total resistance R1 plus R2 plus R3 and so on. So here we can just add them up to get the resistance in this path here. And we can combine them. So 4 plus 2, that's 6 ohms. We can interchange that into a simpler resistance or resistor here. The combination of resistance 2 and 3, and that is 6 ohms. And look at this. This is now a parallel circuit. Right? So the next step is, of course, solve using the parallel circuit method. You just need to do the same thing what we did a while ago, and that's it. That's how you solve this kind of circuits, the complex circuits. Make the complex circuit simple first, and once it shows the simplest form, if it is now parallel circuit, do the parallel circuit method. And the same thing for this one as well. Look at this. This looks like a series circuit, right? So it means we can combine this R1 and R2 to make the entire thing a series circuit, to make them simple. But the only thing is it's hard for us to combine these two because they are parallel at the very beginning. Of course, if they are parallel at the very beginning, you need to follow the method in the parallel to combine the R's. And we're going to use this. So instead of R total, you put here, we're going to put R of 1 and 2. So we're gonna combine the R1 and R2 to make this as one resistor. So this is the formula. So 1 over 5 for the R1 and 1 over 3 for the R2. Okay, it's the reciprocal. And then solve this. What is the LCD of 5 and 3? It's 15. So 15 divided by 5, that's 3 times 1. We have 3 on top. And 15 divided by 3, that's 5 times 1. And we have 5 on top. Okay, and since they have now the same denominator, we can now add them up. 3 plus 5, that's 8. So we have 1 over R1 and 2 equal to 8 over 15. And again, this is not yet the answer of R1 and 2. We need to flip them. And 15 is now on top and 8 at the bottom. Simplify. 15 divided by 8, that is 1.88 ohms. So this entire thing will not turn into one resistor that is equivalent to 1.88 ohms. And that is now the series circuit. Right? And if it is now the series circuit, the next step is to solve using the series circuit method. The one that we did a while ago. And that's it. That's how you do the complex circuits. If you encounter those, of course, turn them into a simple circuit first before you solve them. So you can get the V total, I total, and R total, and you're going to use that for the rest of the components afterwards.